Well, based upon the folks that are on here, we have to say good morning, good afternoon, and good evening, because we've got people from all around the world joining us today, which is wonderful yet again. So we wanted to talk to everybody about the AP4C and how you can use that with low vapor pressure materials. So we will go through kind of the operations and a little bit of other things here, but we just wanted to first welcome you all here. My name is Christina Baxter, and I am the owner of Emergency Response Tips, which is a US-based company where we kind of develop practical tools for emergency response. And one of the programs that we work with a lot, obviously, is the AP4C, because it's so easy to use and applicable across everything that we do in the emergency response community from a hazmat perspective. So I'm going to go back and forth, introduce you to Scott Hartley from ProEngine. And Scott, over to you.
Thanks, Christina. So my name is Scott Hartley. So I'm the CEO of ProEngine Inc. So we do make chemical detection and biological detection equipment. The main purpose of these webinars is really just to provide an educational forum for customers, just as you're facing a variety of new threats, which we'll be talking about some of those today, but then also just to educate people on the use and operations and how to solve some of these challenges that you have with low vapor pressure materials, which is what we're talking about today.
Okay, and for all of our partners who have joined us, if you have questions as we go along, there is a questions section on your GoToWebinar screen where you can type in a question, and I'll try to watch those, but I get carried away when we're teaching this stuff, so we may miss it just a little bit and come back to you. So I'm going to turn off my camera and we'll get started. And I just want to check one thing, make sure that we are actually recording. Okay, yes, we are recording. Just for everybody's background, we are recording this, and that way we will have this available for you to go through and watch later. And if you want to share it with your teams, that's wonderful as well. So just a little bit of background here on how we are going to do this. So as you know, ProEngine Academy is where we do all of the training type of materials in these webinars through ProEngine in France, the mothership for everybody. Now, with that, there are a variety of different webinars available to you, free, as well as application notes and technology notes on the different types of things that are out there, not only on the ProEngine AP4C and other detectors that are available, but also how it fits into your whole emergency response toolbox of kit. So instead of just focusing on the one detector, showing you with all your other detectors where it fits and how these things work together as a toolbox approach. So we'll talk about that more today as we go into the application section. But we're going to start off, we kind of divided it out today to talk first about the technology, then we'll go into the modes of operation, whether we're doing gas, vapor, aerosol, or we're going to do solid and liquid testing. Then a little bit about the sampling interface. For those of you who have used the AP4C in the past, we're going to talk about the S4PE, which was the original sampler, as well as the S4PF, which is the new sampler with the higher temperature regime. And Scott will go into why that's really important. And then we'll go into some applications, both with traditional agents and non-traditional agents and other emerging threats that are out there. So with that, I'm going to turn it over to Scott to start in on the technology itself.
Thanks, Christina. So the AP4C utilizes flame photometric detection. It can also be referred to as atomic emission spectroscopy. I like to personally refer to it as flame spectroscopy. It kind of can be under a bunch of different names. It is a common instrument. So if you go to pretty much any chemistry department at a university, a lot of testing laboratories, they will have these machines. But these machines are very large, so they fit larger than my desk that I'm sitting on right now. But they use the same process that we're doing. Kind of ProEngine's claim to fame, or where it's done, is our ability to miniaturize it into a much smaller form factor and to militarize it from the standpoint of making sure that it's not just something that it's something you can carry onto the field and drop and operate at high temperatures and low temperatures and other things like that. The process itself works on a similar method that, like I like to say, with fireworks. So we had July 4th, and how they work with fireworks is you basically put known metals or materials into that firework, and you apply an energy source, which in this case is an explosion, and they use the metals inside to get the certain colors that they're looking for. So we're kind of working on the opposite principle of that, where we are collecting the spectral information. If you go to the next slide, we'll talk a little bit, or you can kind of see what that is that we're applying energy source. In this case, we're applying a hydrogen flame. You could, in theory, apply an electrical current. You could apply an explosion, as we talked to, or any sort of energy source, which gets to the point of exciting the atoms. So if you excite the atoms in the spaces, so for things that they come to their higher state, when they relax, they actually will produce spectral photons. And if you collect that information, you can then use that to, if you know how to use the information, each element has a unique response specific to that element and that element only. So there's no false positives with it. So that spectral response is specific to that element and that element only. So if you're able to collect that information and analyze it, you can use that to identify. So it's both a quantitative and qualitative measure, from the standpoint that the more atoms that are present, the more light that's produced. The more light that's produced is directly attributed, so it's a direct one-to-one relationship. That's allow us to determine concentration levels as well. So the way I kind of like to talk about is your gold standard of detection is your gas chromatograph, gas spectroscopy, mass spectroscopy, GC mass spec. We're doing spectroscopy, but we're doing truncated. So we're focusing in on core elements, but we're able to identify those extremely fast. So we're doing it multiple times a second, giving you an output either every 1 or 2 seconds, depending on the type of detector that we're operating on with that. But we're looking for core materials or functional groups, not the large full compounds. But what the device is telling you, you can trust. So there's no false positives. So if we're seeing those elements come through, if they're present in the airstream, we will be able to identify them as long as it's above the trigger threshold that we set on the detector. And we'll talk a little bit more about that. So we have a short video, which is the next slide, which will kind of walk through what's going on inside the detector. So we can kind of run on that really quick on that. So what you're seeing here is kind of a blow away of what's occurring inside the detector or in any sort of machine similar to that. In this case, we have what you're seeing here, which is opening up right now, as the pre-burner. So we do operate, or we have the ability to operate in hydrocarbon environments. So we have a protective pre-burner that keeps the flame from coming. If you have hydrocarbon materials coming outside of it, it's kind of similar to a silencer on a weapon. And then you get to the hydrogen flame. So the hydrogen flame is the key element that we need that's going to excite that incoming airstream. Now, if you notice, there are no filters from coming in from the airstream, and we're continuously sampling. So that's the reason why we are able to do aerosols, because there's no filter or blocking of that. And you can kind of see, based upon the elements that are coming through, you're getting a color or a different change in response. So we have a series of filters that are inside there, and then we're using CMOS technology. So what CMOS technology allows us to do is it converts the physical light into electronics, or something that we can use a processor to analyze and look for the specific fingerprint of those elements that we're interested in matching. And that's kind of one of the key aspects, is our ability to do that simultaneously with multiple channels. So we can, each channel is independent, and you can have a hit on multiple channels at the same time. So that's part of the other part of the science with it. And just with the advances in CMOS technology, it allows us to then do that spectral analysis and determine exactly the elements that are needed inside the material. You can go to the next slide. And I think you're taking over now, Christina.
Yeah, and so we put this one together just kind of to show you that there are several different modes of operation where we use the AP4C. So what most people are most familiar with is using the AP4C with its standard vapor phase inlet on it. And in that case, we're generally trying to capture the sample right above or right beside where the sample is. In a regular gas environment, quick, easy, right? Because we can walk around with the detector, and because it measures at such ultra low levels, we can find that sample pretty easily. Now, obviously, our best bet is to be measuring in the areas where we think the sample might be. So we're not going to just measure right at waist level. We're going to measure at waist level. We're going to measure down towards the floor where most chemicals actually go. And then we're going to measure up at ceilings and around door openings and things of that nature as well. Mainly that allows us to get the different vapor densities and looking at where chemicals land. So remember, there are only 14 different gases that are actually lighter than air. So when we start talking about where we're going to sample, we have to remember where the gas is going to go. And if there's only 14 that are lighter than air, then that means the rest of the gases are going to be heavier and down around our feet. Now, the other thing we have to remember is the vapor pressure of the chemicals. So we may have chemicals that don't have a lot of vapor pressure, but they might have some. And in that case, I like to use, that's why the picture here has a filter. I carry around in my sampling kit collapsible filters. And with that, I'll just pop the filter up, set it on a little bit above the material, knowing that most of the vapors are going to stick close to the ground. So I don't measure out of the top of the filter here, but I actually measure, it's a funnel, sorry, but I actually will set it there, let it start to build up some headspace underneath it so that the gas vapors are kind of being trapped there. Then I'll lift it up and measure under there. And that allows me to get access to some sample that, if it's got a lower vapor pressure, allows me to kind of build up a little bit of material there for me. So if I'm doing regular vapor phase, that might be something like ammonia. It's easy, it's everywhere. Even hydrogen cyanide, even hydrogen sulfide is pretty easy to do. But if I want to do something, let's say like VX, it has a very low vapor pressure. And that vapor pressure means that I can have it sitting on the counter all day long, and it's not going to affect me unless I go and interact with it. And so in this case, I would have that VX sitting there, and we would see, God forbid, if you had enough that so you could see it, you would have a small oily drop on a counter. I would set the funnel over that and let it sit for a couple of minutes, and then I would measure underneath it. And that gives us a much better chance. And you'll see some of this in the videos that we're going to show you as we go along. Now, the last step is things like even like malathion, one of our pesticides that we deal with. That one has a very low vapor pressure. And as a general rule, we're measuring along a surface. The same type of thing might happen if we had fentanyl. Fentanyl we can measure in the air, and not as a vapor, but as an aerosol if it's still dispersed in the air. But once it's all settled out on surfaces, we would have to come along and use what we all lovingly call the crack pipe, but that is the thermal desorption unit. And what you would do is take your sample across that surface, you're gathering the sample, and then that sample comes over and you thermally desorb it off into the AP4C. And that's where the pipe fitting goes in. So those are the different ways that we can measure. So solids and liquids, as well as gases and aerosols, and then those heavy gases or those materials that have very low vapor pressure, we may do as a headspace sample. So just to show you how this works in the technique for sampling,
swipe a 10 by 10 centimeters area with the S4PE to sample a spot that could be contaminated with hazardous chemical.
One of the keys here is to make sure you're getting good coverage of the area where you think you might have a sample. The operator can
also collect sample from suspicious object or visible trace of chemical agent. Sample can also be collected directly off the skin of victims. Insert and hold the S4PE on the sampling pipe of the AP4C detector. Hold the trigger to heat the collected sample until an alarm pops up on the display. Release the trigger as soon as an alarm appears on the display to avoid excessive contamination of the AP4C. Otherwise, release the trigger after about 10 seconds if no agent has been detected.
Now, one thing I want to bring to your attention here, if you did not have one of the sampling devices on the front end of that sampler and you went to squeeze the trigger, nothing would happen. And what that means is, unless you complete the circuit by putting your sampling interface on there, your sample collecting device, it is not going to heat up. And that's good because that keeps you, it says fail safe to make sure you don't get burnt yourself. Okay. The other thing to remember is this is the S4PE sampler. If we switch to the S4PF, the new sampler, you have a 20-second max time versus a 10-second max. You still are going to pull the sample away after you thermally desorb it off of there. And so a lot of times when we think about traditional things that you see at like airport crossings where you have a swipe that you put into a heater that thermally desorbs the sample off, this is the same type of approach. You're doing a thermal desorption of a sampler, but you're using a device that is much more accurate and can collect a lot more material. And with that said, I'm going to pass this back over to Scott and let him show you the difference in how this works.
So what we're going to show you is right before we start, because there'll be some voiceover there, we're going to show you 3 different materials. So each of the sarin, mustard, and VX. So each of these have a very distinct and different response. So they're going to hit on different channels. So the sarin and the VX will primarily hit on your phosphorus channel, and your mustard will hit on your sulfur channel based on the chemistry in them. But they also have vapor pressure. So they have varying differences in vapor pressure. So we're going to talk a little bit more about this later on when it comes to chemical warfare agents or pharmaceutical-based agents that you're dealing with right now. Your vapor pressure of the material becomes a very important consideration because that's going to drive your collection efficiency. It's also going to drive the amount of atoms that you have available to come out. And it also is kind of the driver behind why are certain chemical warfare agents area denial versus anti-personnel. So ones that are anti-personnel are, like I like to say, is they can come out and bite you, so they can get to you a little bit quicker, versus other ones want to just kind of hang out at the ground or wherever they're deposited. So what we're going to see here is just the amount of vapor pressure and the amount of atoms and the response that you'll see with it. So you can run it right now.
As we noticed before, the detection of sarin was almost immediate, but it took longer to pick up mustard and VX agent. Furthermore, the VX response was limited to 2 bars on the display. This detection speed matches the volatility of the agents. The lower the vapor pressure, the longer it takes to emit enough vapor to be detected. Again, this is not specific to the AP4C detector. Any detection system would encounter the same physical reality. The different thresholds of the phosphorus and sulfur channel also explains the lack of response on the sulfur channel during the VX analysis. Indeed, the phosphorus channel is 50 times more sensitive than the VX channel.
And that does mean sulfur channel, not VX
After
channel.
the initial release, the VX agent was slowly emitting vapor until the concentration was sufficient to trigger the first bar on the phosphorus channel. However, the vapor concentration was not enough to set off a response on the sulfur channel due to the higher threshold on this channel. As we noticed before,
I'm going to go ahead and run this one, Scott.
Yep, go right ahead.
fortunately, the S4PE sampling device is designed to sample persistent agents and chemicals with low vapor pressure. The S4PE heats up the sample to reach enough vapor concentration for analysis. After heating VX with the S4PE sampler, the agent releases enough vapor to be detected on the phosphorus and sulfur channel.
And one thing, just before we go any further, I just want to show people, if they haven't had a chance to see
the S4PE
it,
sampling device.
right there is a great side view of the sampling device being on it. And I didn't know if you want to talk about the metal and how that works. Thanks.
Yeah, I can do that. Yeah, and then what they're just showing with that last video is because VX actually has sulfur and phosphorus components into it, but the trigger level for phosphorus is set really low, basically as low as we can go, which is down to around 2 parts per billion. And because those materials don't release a lot of atoms, you have to have a lot more material or heat it up sufficient to what would most likely be seen in a real world environment in order to release it such that it starts to trigger on those other channels. So you kind of saw that the phosphorus channel got to the point where it starts blinking, which means it's reaching near, it's close to its max that it can see. And then that's when the sulfur starts to come into play because of those differences in trigger threshold. So now I want to talk to you a little bit about the differences between the S4PE and the S4PF. So the S4PF is the newer device. Now, if you look at them, one is green, one is black. They look relatively similar, but there are a lot of differences associated with that, and that's what's driving the solution. So the F really stands for fentanyl. So one of the challenges, or because of some of these new threats that we're seeing and the first responders are coming in touch with, is that if you look at the melting temperatures of these materials, or because they're just very persistent, you need a lot more energy or more higher temperature in order for us to get an effect on them and see them in the detector. So that was the reason behind the S4PF being built. Now, the problem, one of the challenges that you get with higher temperature, yes, it will release more atoms, but you also, if you have too much heat too fast, you can actually caramelize or carbonize some of these materials, which will have an undesirable effect with it. So one of the challenges that we had to do when we were doing the development process is figure out kind of the ramp up of that temperature profile such to minimize that. So for any of you who made caramel, for example, you know, you have that sweet spot where you can't generate too much heat. You have to keep on stirring or else you burn it, right? So it's kind of similar with this. If you heat things up too fast, you can do that. So part of it is the reason why we have the much longer and the higher thing. So the S4PE will give you up to about 350 degrees Fahrenheit. S4PF now will go up to around, I'd say around 520, 530 degrees Fahrenheit. It'll depend on kind of your ambient conditions. Now, we're going to go through some test data that we've done, but because we're evaporating a higher percentage of the material, you're going to have more material available for that. So you can kind of see now the differences where for some of these higher temperature materials, why that's better, because you're able to evaporate a much higher percentage of the materials to be able to do it. Now, you can still get an effect in S4PE. It's just that S4PF will give you a more dynamic range to accomplish that. One additional component is the scrapers had to be totally redesigned for the S4PF. So if you were to take the S4PE scrapers, they do fit on the device, but you actually can melt them because of the excessive temperatures. So we had to change the polymers that we're using on it, as well as we did add a coating kind of to help us pick up materials, those persistent materials on different surfaces, and you'll kind of see that there's a little bit of a benefit in collection efficiency as well. So the overall result is from the higher temperatures, the higher collection efficiencies from testing that we did, is you get 2x performance for HD, you get 7 for VX, and 17 times improvement for some of your A series agents. In this case, A234 which is the least persistent of the three major ones. If you want to go to the next slide, and I'll cover these really quickly. So what we did is we did some testing in an external laboratory in Europe where we looked at two different types of surfaces, so plain glass and aluminum plate. And what we did is we applied material. So in this case, it's VX and A234. So we dissolved it into a solution. We applied that thing so that the solution evaporates off. So we wait till that's completely evaporated off. And then we applied the scraper over that surface. And then we measure the yield of it. So you can see in the case of VX and on glass, you actually get a better collection efficiency with S4PF than you do the S4PE. Next slide, please. So next we looked at the thermal desorption efficiency. So by taking advantage of the higher temperature of the materials, you're able to get more material off of that you do collect. And so the result of that is that you lower your limit of detection. So this would be the limit of detection in combination with the sampling plus the release of the material. So in the case of it, you're proving at least a 10x increase in the sensitivity, and you're lowering the limit of detection down into the nanogram range, which is 200 nanograms is what was measured for A234, which if you look at A230, A232, and A234, A234 has about half as much vapor pressure as A230 and A232. So it's the least persistent of these least persistent agents is probably a way to describe it. Next slide, please. So next we did the same test with VX. So you're seeing about a 7 times improvement of that. So our limited detection in that case is around 400 nanograms is what we were able to determine on. And there is a little bit of a difference depending on the substrate that you use, but pretty close between the two. And then the next slide. Looking at the detection efficiency of that. So what this is driving is if we have a certain amount of material on there, how much of that are we evaporating off? So you can kind of see that in the case of the higher temperature, you are able to drive off more of that material. So you're releasing more atoms into the detector that are then able to be detected for there. So this follows kind of what the science should tell you to be able to be done. Now, interestingly, with the A234, because of its melting temperature, the S4PE actually just doesn't have enough to evaporate that off, but in the case of the higher with S4PF, it does, and you kind of see the amount of material that we're able to evaporate off. Next slide, please. And this is the same thing now looking for with the VX, kind of the same results, much higher, so almost 100% release of all of the atoms that were collected on there. So they measured the amount of material that was on there, and then they measured the amount of material that had been collected through the device for us to be able to determine this. And then the next slide, please. And I think you're taking over now.
I had myself muted. Everybody's dream. Okay, so what I wanted to talk about now was just kind of how these chemical warfare agents evolved, and add in a little bit more detail here. Now, on the top right, you'll see that there are references to a variety of different papers that we've done in See Burning World magazine. So if you want to get more information about the threats themselves and how they work, and detection versus protection versus decontamination, then you can go to these different issues for the 4th generation agents, the pharmaceutical-based agents, and its traditional chemical warfare agents of the See Burning World magazine, which is online and free access. So as we start looking at these, I'm not going to show you the video again of the traditional warfare agents, because that's where we actually started. And Scott said something a little bit earlier with 2 terms that we use oftentimes when we're talking about chemical warfare. We have area denial materials. Those materials are generally the thick, very viscous materials with little vapor pressure. So area denial is on the bottom here of the screen. And what those are meant to do is, in a military context, if you do not have enough troops to cover an entire area, you actually use an area denial material to give you an extra flank. So what happens there is nobody can travel through the area where you apply the material, because it's very persistent. It's going to stay there in the environment and not break down quickly. And if you touch the material or come into direct contact with it, then you are going to have the effects of the chemical. But it's not going to put off a lot of vapor, which means very difficult, very hard to detect for most cases. Now, thankfully, the AP4C can measure all of these in vapor phase, but when you get into the area denial types of materials, you would be far more suited to just pull out an S4PE or S4PF and get a really nice, quick detection. Now, the other ones are the anti-personnel materials. Those are the ones on the top of the screen. And anti-personnel materials tend to have a much higher vapor pressure, with the exception of the newest generation, which are particle-based, which just gets into a little bit different of a threat. But if we go back to World War I, we used gases. Particularly there, they were materials that already existed, and militaries were looking through what they had as they were running out of traditional ammunition and weaponry, and said, you know, we have these materials, they're heavier than air, they're going to push people out of foxholes, we're good. And so they went with these gases. After World War I, they started doing research on materials that were specific to warfare, and that's where the nerve agents, the G series, came out, the sarin, the soman, the tavun, cyclosarin, all of those materials. But in this case, they were liquids that had a relatively high vapor pressure. So just think back to Omshrinkyo in the Tokyo subway in 1995, and you have material that was a liquid in plastic bags that were then punctured, and the vapor came out and filled the subway areas. That's because they had an appreciable vapor pressure, and they still stayed areas that are really easy to detect if you have the right detection capability. Fast forward, we have the 3rd generation of the agents. So the 1st generation was just taking things off the shelf. Second generation was the G series, the first round. The third generation is the G series agents still, but now trying to weaponize them into a way that they could be produced ahead of time and stored in munitions as the last two components and mixed just prior to release. What that does for us is allows it to stay on the shelf and have a shelf life and be able to be made in advance and used in warfare. Thankfully, today, most of the militaries in the world have gone away from using any of these types of materials. Unfortunately, most of the militaries in the world that we're all worried about the most are the ones who did not get rid of it. Now, as we come across all the way to the right on the top bar, we have what are called pharmaceutical-based agents, and we're going to go into those a little bit more in a moment. And those tend to be solid materials. There are two that are liquids, but the issue we have here is instead of being a gas phase approach, these are going to be an aerosol approach. And what we mean by an aerosol is they are solids and sometimes liquids, but they're dispersed in such a size in an air matrix that they take on the movement characteristics of a gas, but they retain their properties as a solid or a liquid. So now you have what's not necessarily a gas, it's not a vapor coming off of a liquid, but you have an aerosol. And when you look at your inventory of detectors that you have available to you today, the problem that you'll see is any of the detectors that have a filter on the front end cannot measure aerosols. And that filter is blocking the aerosols from reaching the inlet of the instrument. In reality, today, the only two detectors that we're having success with in the measurement of aerosols are the AP4C for low-level detection and the MX908 for identification of the materials. Everything else, we've got to do something to get those aerosols into another form to be able to measure. Or if you're talking about Raman and infrared, you're going to collect a lot of sample. You're going to have at least milligrams of sample to be able to measure it on those devices, which when we're talking about the fourth generation of agents, the last thing I want is a milligram of the material around. So that kind of puts us in a bind. Now I'm going to go through the pharmaceutical-based agents first, and then I'll have Scott go through the fourth generation agents as they relate to us. Now the pharmaceutical-based agents are one of our high threat material types right now, mainly due to availability of the materials. Now, this is the only time we ever get to say thank you to the people down south of the border that are shipping all of our drugs up to us, because in this case, the opioids, if we go back about 5 years, we were getting opioids directly in from China into the United States that were coming in very high purity, 97% and higher, which made them an extreme threat from both just people who were working with them and as a terrorism material, because the amount of material was such high purity that you could get a lethal dose inadvertently. Now today, most of it's coming in via the cartels in South America and Central America. And what happens there is that the cartels are cutting the drug before it comes to the United States. They can get the most money out of the drugs. So we have materials coming into the United States that are now, on average, less than 7% and oftentimes less than 3%. And what that does for us is it minimizes the accidental issues. It also minimizes the amount of material that would be suitable for a large-scale attack without having to do some extra work. Now, with that said, there are still events occurring around the United States and Canada where we have taken into evidence large amounts of high purity material. Case in point, it was only a couple months ago now where many kilograms of fentanyl was confiscated in Worcester, Massachusetts. Unfortunately, New England in the United States is a hotbed for a lot of this activity still. I know Mikey Comer is on here, so you guys had the fun of getting that material out in Worcester, which thankfully was taken into consideration because now it's off the streets and it was in high purity. So don't be shocked to find you sometimes will get that high purity material still. Now, as we look at these materials, most of us only think about the opioids because of the high interest level that they're given in the opioid epidemic ongoing. But don't forget that there are many different types of pharmaceutical-based agents. The opioids are just one of those. The ones that we tend to look at as pharmaceutical-based agents are things that were used in the human medical community or in the veterinary medical community that have been used as anesthetics. And so what we're looking at here are materials that can take you out of the fight temporarily as a form of incapacitating agent, not necessarily intended to kill, but to temporarily take you out of the fight. Unfortunately, oftentimes the side effect of that is you do die. We saw this in 2002 with the issues that were ongoing over in Russia with the Chechen rebel crisis in the theater, where the hostages were tried to take out with a mixture of carfentanil and remifentanil, but ended up losing about 10% of the civilian population as well that was in the theater. As we look at these different materials, just remember that most of these are solids. Propofol and cefaclorine can also be liquids, but with that said, they are all distributed as aerosols, which makes it very difficult to detect. Now, also keep in mind that as we are looking at these materials, especially those that are particles, we have to remember that those particles, for the first 30 minutes that they're in air, because of their organic molecule nature, will take on electrostatic effects. And so all that really means is every particle becomes like a little miniature magnet. And so as they go airborne, if they have opposite charges, the particles next to each other, they'll come together, agglomerate, and make a larger particle, which falls out of the air because now it's too heavy. But if they have the same charge, as those particles come together, they'll push off one another and go back airborne. And what that does is keep those particles airborne for lengths of time. Now, if you were in a room where there was no airflow, you had the ventilation turned off, you had no openings of doors or anything like that, your average particle from fentanyl, which is around 2 microns in size, would take between 1.5 to 12 hours to all settle out of the air. Unfortunately, every time you open up the air into that space, now you've increased the ability of those things to go airborne again. Remember, every time they go airborne, more and more will come out of the air as they come together and make larger particles. However, what we have to look at here is in a turbulent air environment, these particles will stay airborne for multiple days. You'll lose about half of its population every 12 hours, which is kind of crazy. And it explains some of the different things that we had happening when we were first doing studies in the laboratory on fentanyl, where the fentanyl stayed airborne for days upon days. And the way that we actually got it out of the air was to increase the humidity in the space. And as we increase the humidity, those particles would take on more and more water weight and fall out of the air. So be very careful about turbulent airflow. Now, the good news here, when we talk about fentanyl as a threat material, there was a lot of misinformation out there to begin with in this entire event. Fentanyl as a dermal absorption material. Will fentanyl go through the skin? Absolutely. If given a long enough time period, a high enough concentration, in other factors involved, fentanyl can go through the skin. But in an operational environment that we see fentanyl in, and in the timeline that we work with, it's very limited the amount that could ever get into your skin. And that amount would take hours to get through, and the amount would not be enough to give you a lethal effect in any way. And in most cases, you would never even know you had it. Now, when we're talking about things being airborne as well. If you're wearing respiratory protection, even if that respiratory protection is an air purifying respirator, it will pull out the materials because there's a P100 filter in there that will remove 99.97% of the particles of these sizes. If you have an SCBA on, you're like 99.99997%. And so you're pretty good. Now, even if you were in this environment, you would have to be very careful about the amount you breathed in, especially if it's a milling laboratory. But incidental, if you were just working with somebody, your likelihood of going down because of a fentanyl exposure is very, very low. Now, I just want to show you how this works. And this right here is fentanyl and methanol. As the methanol evaporates off, you see the fentanyl is going airborne. And it's naturally going airborne, and that's just its electrostatic effects. So watch again. We're waiting for that nitrogen channel to clear out. It's right there, the second channel. And now you're going to see us put another drop in once this low bar of the nitrogen goes away. And as that second drop is put in, remember, this is just methanol. The methanol quickly evaporates, leaving some of those particles uncovered, and then they go airborne on their own. So that's self-aerosolization, and that's 100% based upon the electrostatic effects of fentanyl. This is what would be considered fentanyl vapor. In reality, that's a misnomer because fentanyl actually degrades at higher temperatures. And so you don't actually get fentanyl vapor. You get other things you shouldn't be breathing in. But now you can see it hitting here. But the problem here is ultra high temperature to get that to happen. So there is no such thing in the real world as vapor phase fentanyl. What you have is aerosolized fentanyl, which means, again, all those other detection technologies that have filters on the front are going to completely miss this threat. And Scott, I'm going to turn it over to you for the A series.
Sorry, I was on mute again. So just one additional point from that last video, you can kind of see where we put the fentanyl onto that hot plate. You see some of that carbonization that's occurring. It actually starts as a white powder and then goes down. So that part of that hot plate testing was used to help us identify kind of the flow rate or the ramp up temperature on some of the fentanyl and helping design the S4PF and making sure that it works well with that. So now changing topics to the fourth generation agents. So these were ones that kind of like well-known secrets that we couldn't talk about very much in open forums, but then all of a sudden when they were used a couple years ago in 2018 in Salisbury, we were able to now discuss them in more detail with it. So there are a number of different classes. The research on them had been going on since the 80s. With it, our first knowledge about it was due to a lab accident at their laboratory in Russia where they're doing a lot of it. And then a release of, and then also a person that immigrated to the United States and presented a book on it. So they gave us some more information about it with it. So they're mostly, what we know about them is they're organophosphate-based materials. The majority of them are. They're just new variants of them. They're more potent, but they have extremely low vapor pressure. They can present as solids and they can present as liquids, or they can be binary mixtures of them. They primarily have been used as targeted assassination tools. They would also be extremely good area denial weapons if so used that way. Their use primarily has been just as long as you don't infringe on Putin's money-making opportunities or speak about him on any sort of outdoor environments and present videos on it, usually pretty safe from being exposed to them. But they do exist, and if you actually read up on some of how these things were implemented, it's pretty high-level assassination attempts, whereas multiple people and multiple things that they targeted. It's very interesting reading if you actually want to get into it. But again, they're primarily means of attacking people, and how they've been done is primarily through the skin. So they're percutaneous. So if you do get it on your skin, they do have a pathway and they're fairly efficient in going through the skin. Now, if you do get it into your respiratory system, they're going to take you down extremely quick, but the chance of them getting into your respiratory system is a lot harder just because they're super super low vapor pressures, and they just don't want to come out and bite you very easily. But if you do happen to put it up near your face or other things like that, then they will come and have almost a very, very fast response time on them. You want to go to the next slide, please? So what we know as far as your onset of symptoms, it depends if it's where and how it's applied with it. It does prefer humid systems. So like when they used it with Navalny, they put it into his underwear. and to be able, and that's the means of doing it. And they knew how long, they knew he was going to be on a flight, and they knew the duration of how much to put in there. But you're primarily going to be presenting with your pinpoint pupils, with your salivation and loss of consciousness. A lot of times it can present itself potentially as similar response to what you would get with fentanyl as well. So that sometimes can cause a misuse of a response with people. But in this case, the main thing is inhalation is almost immediate versus dermal. It can take long periods of time to go through, but it does fairly efficiently go through your skin. And if you compared it against a PBA, it is more efficient dermal than a PBA would be. Next slide, please.
And Scott, I just want to bring up right quick while we're on this one. It is the hypersalivation and the perspiration that bring the difference between when you're observing an organophosphate exposure versus observing a opioid exposure. So you both can get the pinpoint pupils, so you can't use that as that delineation anymore. It's that extreme sweating and salivation that really pull it apart.
Yep, thanks. Yeah, so they both will have meiosis associated with them. So what we're doing here, so even though your opioids, your fourth generation agents have extremely low vapor pressures, they still can off gas. And so this is just showing, and you can start the video because it'll take a little while to set. What we're doing is we're testing A230, A232, and A234 in an open environment. So it's going to primarily hit, even though it has nitrogen in it, it's going to hit like your phosphorus channel just because of the amount of material that's present with it. What you see is the actual A series is in the smaller test tube that's in the larger test tube. With it, and what you're going to see is the release of it, and I'll kind of, you can hear it talk through there, but it walk through here. So what we're going to be testing is A230, A232, and A234 on there. And you can kind of see it's got released, and then you start to get either 1 to 2 bars.
Concentration of 20 parts per billion. The best way to pick up these agents would be to use the S4P sampler, especially at low temperature when they would barely release any vapor.
So again, the main thing with these is, even though if they are in milliliter quantities, which is still not much, but in some cases milliliters would be a lot for some of the materials here, when they are released, you see that smaller test tube, it's coming there. So this is just pure headspace with it, but even though the vapor pressures are extremely low, they still are off gassing. So there's a little bit of a misnomer. Most people think, hey, they're so low, there's nothing coming off. No, there is, but you have to have extremely sensitive detector to be able to see it. So the levels that we're seeing that you will see in these concentrations are down into the single parts per billion. So between 2 to 10 up to maybe in the low teens. So it's extremely low concentration. So that would equate to 1 bar on the detector up to 2 bars on the detector. Again, the part that's not, we do present data on the detector in the form of bar levels for ease of use and operation, but we are still storing the actual concentration levels on the detector, and that information can be taken off the detector if need be with it. But just to let you know that these are extremely low concentrations, so probably this is the only detector that could see it at this range, other than maybe a GC, a gas chromatograph machine in a laboratory setting could see it. But in those sort of cases, this is a field indication that something is occurring there and allowing you to know that it's occurring. But then also just to show you the vapor pressure differences associated with some of these materials.
And one thing I want to bring on here, Scott, is just because it's not very often that you see the way this is done. And I wanted everybody to see that there's what's sand in there. And the reason the sand is in there is to make sure that the material in that container does not heat up. And because the last thing we wanted to do in the environment in the hood was to actually increase the vapor pressure. So we wanted to keep it very static at room temperature. And so that sand bath is what we call it, is there to give us a very constant temperature and make sure that we aren't increasing the vapor at all. But still being able to see it, which was really phenomenal to be able to test.
Yeah, and what you can't tell from the actual videos, this has voiceover on it, but if you were to hear the actual video testing, it's like they're pulling, so these they're in, obviously a vent hood, and this is like a vent hood that sounds like a jet engine's pulling it. So they're pulling high CFM outside of the vent hoods in there. So it's also to maintain consistent temperature through the full amount of the test.
Most nerve
And you're right, there's we've not come across another detector that can real-time measure this. If we were to do a GC mass spec, we could do that in a laboratory environment, but you're talking, the newer fast GCs could probably do a separation and identification in about 6 minutes. But we're talking even A234, which is very low vapor pressure, we're talking about detecting in 40 seconds here, which is pretty cool. Now, I'm going to go in and talk about a couple of different emerging threats. And while these ones do not require the use in a standard way of the S4PE, S4PF interface, I just wanted to bring these up to let you know that there are things that we are seeing and doing right now in this world. So the first one is the irritants. We have had a huge increase in the use of irritants, and specifically homemade irritants in North America in the last few years. Now, what we're seeing right now is people trying to extract capsaicin, whether they're doing it straight from cayenne pepper powder, or they're doing it from hot peppers that they're growing, ghost peppers, those types of things, or if they're just going and buying it. What they end up doing is making a pepper spray that in many cases is stronger than even law enforcement can buy in the United States. And so we're up against pepper sprays, which are higher levels than we've ever seen. Added to that is that while they're extracting them out in isopropyl alcohol, they're letting that alcohol evaporate off until they get a thick condensed sludge pretty much. And then they're reconstituting it with oil. So that could be vegetable oil, olive oil, any of those things. But what it does is for our responders, if they get sprayed with this, you can't just wash it off your face with water. If you use just water, it'll spread the oil and spread the burn, making it far worse. Now, to add a little bit more to that, what you're seeing now is people making homemade sprayers to be able to spray this. And so before, when they were using sprayers that were much less capable, we were only seeing that spray go out 3 to 4 feet. With the newer sprayers that they're making, that you can see here on the right, they are easily sending this out 25 feet. And so we could be quite a way distance from an officer, and they can get sprayed in the face still with this material. And then you go to wash it off with water, and you just spread the burn across the face. Keeping in mind that these materials are stronger than the law enforcement grade, and that creates quite the problem. Now, the good news is the AP4C can easily and quickly detect this in aerosol form straight off the nitrogen channel. Same type of thing. The MX908 can also, in aerosol mode, detect, and it'll say pepper spray. And that's covering, what it's doing is both detectors are measuring capsaicin. And so on the AP4C, we're measuring it at a lower level, but we're telling you it's a nitrogen-based material, and we can tell you how much is there. Then you can go and use your MX908 to tell you that, hey, it's pepper spray, unique identification. It won't tell you which type of pepper spray at this time. Right now, we're just going capsaicin across the board. But it does give you the way to measure pepper sprays in the field and quickly adjudicate those types of calls, especially if it gets back to the times that we used to have when people would spray it into the mall air interfaces and things and be a problem.
Yeah,
the other
Christine,
one I want, oh, yeah.
Yeah, and just to add to that, I mean, we've seen examples, a lot of times there are inadvertent releases in like a school or something like that. So the AP4C is just good from letting you know, is it aerosolized anymore or not, which is, the primary threat, because you just want to make sure, is it safe for them to go back into that area after it's been inadvertently released. So that, in this case, the aerosol is the threat, the primary threat, and then the detector is able to identify that fairly quickly if it's there or not for
Absolutely.
Mitigation.
And frankly, if it was a school, before I put people back in, I would be making sure nothing was measurable in the air, but then I would also be using the scraper on the area around that, on the surfaces, to make sure there wasn't any sitting on surfaces as well. because what happens is you may not see it. It may not be enough for you to see it all, but you may touch and transfer it to your mucous membranes and you'll know.
Yep.
And you'll know for quite a while.
Or re-aerosolizing it, because a lot of times it'll, float out of the air and go towards the ground, but then it can be re-aerosolized if not taken care of.
Yeah, and this is one that we're coming across more and more every day. And unfortunately, we didn't have any ways outside of, if everybody remembers back to the APD 2000 Smith's old detector, that none of us have working ones anymore, but that used to be the one thing we used it for, is we kept it around for pepper sprays. Now, the other threat that I wanted to make sure everybody was aware of is the binary devices. And so traditionally, these were called MOOC talkers. That center picture is a traditional MOOC talker design where you would have sodium or potassium cyanide in solution, and then you would have some acids, and down the middle, you would have an explosive charge. All of these would be contained in an outer container to force the mixing once you broke the glass. What you're seeing today is more of a Molotov cocktail approach to those, where the one would be the sodium cyanide or potassium cyanide in solution. The other bottle would be an acid, and then they duct tape the crap out of them together. And so when they throw that, it breaks the glass, forcing the reaction between the two, and the gas is able to get out that's produced. So these produce anything from, if you're talking to cyanides, you've got hydrogen cyanide gas coming out. We've also seen it discussed with using the sulfides, so they can have things like lime sulfur, or they can use things like dandruff shampoos in an acid and produce hydrogen sulfide. They can also make phosphine using aluminum phosphide or zinc phosphide insecticides. Those are both rodenticides that you can get pretty easily. And then, of course, going the old route of your chlorine pool chemicals and trying to do that approach. Again, each of these in the newer design are not as effective. However, they still create the mayhem that they're looking for. And if you just go back to the Lone Mujahid, which was on a Telegram channel, that goes through and tells you the exact amounts to use. And if you actually had 750 grams of sulfur or potassium cyanide, sodium or potassium cyanide, and you added a liter of acid, you are producing a tremendous amount of gas. And this is what you see in Afghanistan at the girls' female schools where they have the cyanide devices. It would be that center device is what they're using there. Now, with that said, just a reminder to everybody, while they're called gas-forming reactions, the first thing you can do is try to minimize the spread of the gas. These gases tend to be heavier than air, with the exception of hydrogen cyanide, which pretty much mixes perfectly with air. And so putting anything you have available over it to minimize that spread is helpful to allow you to get evacuations ongoing. Now, obviously, if you have something like a trash can you can put over it, even better, because you may not be affecting the evidence quality. But if you have to, then you end up putting a plastic bag or something, just dropping it on it. And you're not going to change the speed of the reaction. You're not going to change the rate of the gas release. What you're doing is minimizing the spread while you execute the evacuations. Now, with that said, just remembering in this column, 2 in from the right is the potassium cyanide approach, and then 1 in is the aluminum sulfide. And what we're trying to show you here is that just in a traditional subway, train, or bus, the amounts that you need to execute a lethal limit are very low. And so when you're talking about somebody doing an event like this, if they only had to have 200 grams of sodium cyanide or potassium cyanide to execute this in a subway car, we have a problem, and we need to be able to measure this and keep up with it. And so those are the types of things we're up against. The nice thing here is with all the different threats that we see, the most common ones are sodium cyanide or hydrogen cyanide, which we'll see in the nitrogen channel. The phosphines being produced, you'll see on the phosphorus channel. The sulfides, you'll see on the sulfur channel. The only one of all the different ones we've talked about over the years that we don't see is chlorine, okay? And most of that we can actually measure just using wet pH paper. And so wet pH paper will actually turn red, then blue, and then bleach out with chlorine. And so you'll actually have pH paper that turns white. And so that will give you a quick and easy identification that you have that, even at the levels that you're producing in these types of events. Now, with that said, just remember, I know a lot of us do have our electrochemical cells, And I just want to remind you that these things take a lot of time. So a hydrogen cyanide sensor on your electrochemical cell takes 200 seconds to respond and give you a quantitative measure. So if we're talking 1 to 2 seconds on our AP4C versus 200 seconds on my hydrogen cyanide, I'm going to use both, really, if you're coming to me. I'm going to use my AP4C to quickly identify it, and I'm going to keep that other one sitting there to continuously monitor it as well. And that way I can figure out 2 different forms of detection, how it's happening. So just remember, with the materials we're looking at, depending upon which sensor you have in your system, your hydrogen cyanide takes around 200 seconds, your hydrogen sulfide around 35, your phosphine around 60, and your chlorine around 30. But each does provide a capability that is working along with our other sets. With that, I was going to open it up for some questions, because we're right at about an hour. And so I know I had a couple of different questions that showed up. Let me see if I can pop those out. Let's see. The main one was just, are we going to be able to have this material available for people to watch? Absolutely. All of these are recorded, and you can get any of the webinars and information through the ProEngine Academy, whether it is directly through either Scott or Gautier or others on their team. And you can get it on their website as well, and on their YouTube channel. So all of these things will be posted and available for you to use as educational materials as we go forward. Obviously, we don't keep.
We'll send out an email to everyone that's that signed up for this with the link. And then we do have, if you go on YouTube and search ProEngine, there is a channel there that has some of the previous webinars that we did and some additional videos that we're producing, and we're going to be adding more to that.
Absolutely. And just got a question from Mike Kimura out of Massachusetts. Have we seen MOOC talkers using potassium permanganate? Yes. So if you go back just to that one slide where I show with the Lone Mujahid out of the Telegram channel, that was one of the first modern releases of how to detailed make a MOOC talker. And in that case, yes, and they used potassium permanganate. 2 different reasons that they use that. One, it's an oxidizer, and an oxidizer will increase the rate of the reaction. And so that's one of the reasons. The second one is when you use potassium permanganate, it creates a purple cloud too. And so instead of having a clear or unseen gas like hydrogen cyanide, you now have the production of a purple gas, which frankly will scare lots of people because there really aren't a lot of purple gases out there. But that is the main reason, is the use of potassium permanganate increases the speed of the reaction by adding an oxidizer. I'm not seeing any more questions. So what I will do is say that if you have more questions, my email and Scott's emails and our phone numbers are on your screen. Okay, and you can always get us that way and let us know of what you had for questions. Now, I just saw another one pop up. Wait a minute, let me pop up there and see what that one was. Okay, we've had 2 separate suicides in the last 18 months using potassium cyanide. Absolutely. Potassium cyanide, generally as an ingestion, is a common suicide route. And one of the things that you have to remember, Reese, when you're dealing with potassium cyanide or even sodium cyanide suicides, especially when they ingest them, is that you are going to bioaccumulate hydrogen cyanide in the body. So there's a couple of different things you may need to do. And you need to talk with your medical examiner before you do these, because a suicide is still a crime scene until proven otherwise, because it's an unintended death. The last thing we want to do is take hydrogen cyanide building up in the body and transport that to a morgue or another place where they may be doing the autopsy. With that said, what we generally recommend, the decon for the outside the body is just fresh air for hydrogen cyanide. You could take off the clothing and make sure that there's nothing trapped in between the layers of clothing. But you also need to consider what we would consider an inside of the body decontamination. And to do this, we generally take a nasal cannula with 2 liters per minute flow rate of oxygen. So you put it in the nasal cannula approach, crank it up to 2 liters per minute, and let it run for 12 minutes. What we've done in the past is videoed that for the medical examiner, and then take the AP4C and put it right by the mouth, so that as the air is pushed in through the nose, the oxygen, and it's pushed out via the mouth, you're doing 3 air exchanges of the esophagus, the lungs, and the stomach. With an AP4C, it has a fast enough response time that it will see the cyanides being pushed out of the body. If you video that and record it, that will allow the medical examiner to see that. It's much harder to do if you use your electrochemical cell because of the very slow response time. But that is one of the things that you need to think about and pre-coordinate with your medical examiner is on chemical suicides, especially those involving cyanides, where it bioaccumulates in the body. We have had problems in the past where the medical examiner's office, if they don't have a good ventilation system for contaminated remains, then you can get an exposure to the people in the laboratory who are doing the autopsy. So we got to be very careful about that. So thank you, Reese. That's a great one. Okay, with that said, Scott, do you have any more comments or questions on these things for people?
Nothing comes to mind right now.
Okay, well then I'm going to say thank you, and we will follow up with a response to everybody from the webinar system saying thank you for joining. Please reach out to us if you have any questions, and we will do our best to help you with these things. Again, remember, you can always reach out to Scott about the AP4C, and you can reach out to me about any of your detectors. So thank you all. Have a great day and stay safe out there.